Welcome to my Introduction to Networking course, also known as ITN. This is the version 7 material preparing learners for the Cisco CCNA 200-301. Cisco curriculum, everything is owned and copyrighted by them. Welcome to Lesson 5. We're talking about numbering systems. That's going to be the different numbering systems that we're going to be interacting with, like binary, hexadecimal, decimal, and so forth. So the big three are decimal, that's base 10, that's what we're used to counting in. We're going to relate that back to binary, which is base 2, and we're going to talk about hexadecimal, which is base 16. The nice thing is, with decimal, binary, and hexadecimal, all numbers can be represented. There are some numbering systems out there that are not necessarily able to adjust for all numbering systems. So it kind of just depends on what we're trying to accomplish. Octal, for example, base 8, does not allow for representation of all numbers. So I did want to point out there's tons of numbering systems out there. It's just more of a which ones are we going to be able to use? So our first one is our binary numbering system. Binary means ones and zeros. So our decimal numbering system is 0 to 9. Binary is 0 and 1, and they typically refer to these as just bits. 2 bits, 0 or 1. So on a network, everything is broken down into binary bits. That's how our addressing works. Bottom left-hand side, you'll see that we have a bunch of ones and zeros. That is how communication actually flows. However, to make it easier for us humans to read, we convert this back to decimal. That is why the diagram on the right-hand side is showing the decimal versions of those numbers. So an address, you'll notice there are 4 groups of numbers. Each group is actually 8 bits. I want to call that an octet. So there are 4 groups of 8. There are 4 groups, each one being called a different octet. So here we have 192 is an octet 1. 168 is an octet 2, 10 is an octet 3, and the 0 is an octet 4. This is called dotted decimal form, also called dotted notation, or dotted decimal. Kind of just depends on who you're talking to. There is a video talking about converting back and forth, which we've already done that in class. So here is a positional method. In our base 10, if we're dealing with 10 to the power of 0, on the far right it's always going to be 1. If we're dealing with a number in the 2 position, it's going to be 10 to the power of 1, which will be 10. If we're dealing with a number in the 3rd position, same thing. So actually I'm going to get my pen. So if we're dealing with 200, we have a 2 in the 100 spots. That's this area. Because this will be the ones, tens, hundreds. The 4th spot will be the thousands, and so forth. Which we already know that. In binary, we have the same general breakdown. Except in binary, we do everything to the base of 2. 2 to the power of 0 is 1, 2 to the power of 1 is 2, 2 to the power of 2 is 4, and so forth. So if we have a number like 1001, the far right is actually going to be our 1 position. That will be our 2 position, our 4 position, and our 8 position. We basically add up where the 1s are. We would add 8 plus 1, that would be 9. In this spot right here, you'll notice we have 0, 1, 2, 3, 4, 5, 6, 7. So that's our 8 bits. That makes up a octet. we have our positional values 1 through 128 and so forth. So if we have number 1, 1, 0, 0, 0, 0, 0, 0, we'd only add where the ones are. We have 1 in 128 and we have 1 in the 64. 128 plus 64 is 192. So that is our decimal conversion. This is taking a basic binary number and converting it to decimal. I have got tons of videos on these conversions for lots of practice. So if you need additional help with this, check out my playlists. I have binary addition, subtraction, binary math. All of these videos for binary and hexadecimal has already been done. Way more in depth. If we have a few other numbers, here we have 11000000, which we've already done this first one. So now let's do the second one, 10101000. We're going to add 128, we're going to add 32, we're going to add 8. That should be 168. The third number will be 00001011. We add where the ones are, so we add 8 plus 2 plus 1, that'll be 11. And then we can add our fourth number. Our fourth number is a little easier, 00001010. We add 8 and 2, that gives us the number 10. So put those numbers together, that would be 192.168.11.10. That is our conversion from our IP address, this guy right here, to decimal. Because again, the computer knows binary. We know decimal, so there has to be a conversion between the two. For decimal to binary conversions, basically we start with a number and we subtract it. So here we have a chart that basically says we start with the higher number. If we have 8 bits, we already know the largest number can only be 255. Any larger than that will not fit in an 8-bit numbering scheme. So it has to be between 0 and 255 to fit in a 8-bit number block. 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1 is 255. So do keep that in mind. Here's an example. We're converting 168 to binary. Is 168 larger than 128? Yes or no? Yes. Yes, it is. So we get a 1. We now take 168, we minus 128. The remainder is 40. Is 40 greater than 64? No, it is not. We get a 0. Is 40 greater than 32? Yes, it is. So we get a 1. And we subtract it. 40 minus 32 is 8. Is 8 larger than 16? No, it's not. So we get a 0. Is 8 greater than 8? Yes, it is. We get a 1. We now subtract it, and the remainder is 0. Is 0 greater than 4? No, we get a 0. Is 2 greater than 0? No, we get a 0. Is 1 greater than 0? No, we get a 0. So this is how we take 168 and we convert it to binary. It will be 10101000. And again, I have these broken down, lots of examples in other videos in my playlist. If you search for binary or addressing or math, you will find them as other playlists. So routers understand binary. We know decimal, hence the conversion process. Well, the issue is when we have tons of large strings of numbers, it can get kind of confusing. You'll notice IP addresses are broken up into 4 groups of 8. Well, the nice thing is a hexadecimal number is 4 bits. So we're not having to deal with 8 bits, we're having to deal with 4 bits. So there is going to be a nice thing when we talk about our hexadecimal. Hexadecimal is between 0 and F. Basically, we want to represent all numbers between 0 and 15 with a single character. After 9, we have no way to denote the number 10 with a single character, so we did A. So A is actually equal to 10. B is equal to 11, C is equal to 12, D is equal to 13, E is equal to 14, F is equal to 15. That just allows us to reference F, for example, a single character, to the number 15. You'll also notice if we're looking at 4 bits, if they're all 1s, that will be the number 15. That is also equivalent to our F in hexadecimal. So why is hexadecimal important? Hexadecimal is used very heavily in IPv6. That's how IPv6 addresses are actually displayed. They're done in hexadecimal. So we have to know binary for IPv4. We need to know hexadecimal for IPv6. So again, IPv6 are 128 bits in length, which means every 4 bits is represented by a single hexadecimal digit. So it actually takes 32 hexadecimal values to represent a IPv6 number. That's a really large number. We are actually grouping our hexadecimal into groups of 4 numbers, and this will be referred to as a hextet. So this is a hextet. This is the second hextet, third, fourth, fifth, 6th, 7th, and 8th hextet. And again, each hextet is actually 16 numbers. So how do we convert our different numbers to hexadecimal? So for 168, we would convert that into binary, which we've already done. We know that's 10101000. What we can do is we split it into 2 groups of 4, and that gives us our 2 groups of 4. Nice thing is we know hexadecimal is groups of 4. This is the decimal number 10 or the hexadecimal number A. This is the decimal version 8 or the hexadecimal version 8. So 168 in hexadecimal is A8. We can do the same thing. We've done several of these examples already, but what we do is we can convert hexadecimal into strings of 4 bits. Basically, if you have a decimal number, convert it to binary, do groups of 4 bits, and convert that to our hexadecimal numbers. And we can do that back and forth. And that is this chapter in a nutshell. If you have any questions or concerns, please reach out.